Uh, so my name is Sergey Panyukov, as you can see on this screen, and my talk will be about diffusion. So what's a diffusion? The simplest example is just on the slide, as you see here. Let's take two liquids, one over other liquids, with different properties, different density, and so on. Because of the Brownian motion of the particles, these two liquids are mixed together, as you see here, and in the result we get more or less homogeneous liquids, which is a mixture of the two ones. The simplest model which describes the Brownian motion is a random walk. It can be considered as the motion of the drunken man, which is in the right corner of this slide, and let A1, A2, and so on be the steps of this man. The steps are random and they're independent on each other. This independence is that the is first of all and is homogeneous, so that the average of these steps is zero, of all the steps is zero. The distance between the final after n step position and the initial position of the drunken man is the sum of these steps r. If you take r squared, you can see that there are the term a1 squared, a2 squared, but additionally there are a1 times a2 terms. But the average of this term is zero just because the steps are independent on each other. As a result, we get that r squared is equals to n times a squared, where a squared is a average squared size of one step. So that we conclude that the distance of this drunken, or the distance between end to end of the random walk, is proportional to square root of n, the number of steps. At this step, we need to understand the important concept of probability. Consider random events. All random events occur with the same frequency, and so that in this case the probability is the event number divided over the number of all events. In the case when this number of all events tend to infinity. The simplest example, if you toss a coin. In this case, there are two events, head and tails, so that the probability of head and tails is equals to 1/2, and it is the same, of course. So now consider a Brownian motion, and we introduce here in this slide the probability. The probability that the random walk end is at a certain volume delta b. It's ended at this volume, and this probability can be written as the probability distribution Pn and times this volume delta b. So it is proportional to this volume. And this Pn of R is called as a probability distribution. Obviously, since the total probability of all events, that is, the random walk is ended at any point, is 1. So the integral Pn of R times dv is 1. And the average squared distance between n's, it can be calculated from this probability as an integral Pn times r squared. And in the previous slide, we just talking about this value. At this point, let's recognize some mathematical concept. Probably you know that, but I'll repeat it for you. So this is a derivative. The first derivative is defined as the increment of the function when its argument changed by delta x and divided over this delta x, and taking after that the limit delta x tends to 0. This is the first derivative. In addition to it, we can define the second derivative, which is a derivative of the first derivative. It's f2 prime on this slide. By knowing f prime and f2 prime, we may expand our function f of x plus delta x in power of delta x. The coefficients of this expansion is just the first derivative f prime and the second derivative f2 prime. Later on the next slide we will use this equation. So now let's turn to Brownian motion and try to calculate this probability distribution for n steps, so that we consider the Brownian motion of n plus 1 steps, which may be considered as the Brownian motion of n steps with additional step of vector a n plus 1. So the probability of n plus 1 steps is the average over this additional step vector a n plus 1 of the probability of n plus 1 steps. We may calculate this average using the expansion of the function of the previous slide. So the probability Pn, when we expand it, there are three terms. The first one is probability Pn of R. The second is a derivative of this probability, and the last is the second, proportional to the second derivative. After the averaging, we find that since the average of n plus 1 is 0, we get only the first and the last term in this equation. And so that Pn plus 1 equals Pn plus the term proportional to the second derivative of Pn. For large n, we may present this Pn plus 1 minus Pn as the derivative of the distribution function over n, and we get the following equation: dn of Pn equals to a squared over 2 and the second derivative of Pn. This equation is called a differential equation, but it can be easily solved using the knowledge about exponential function. So what is the exponential function? It's e to the power of x. First of all, e is the constant, which is 2.71 and so on, and this function has the following properties: that e to the power x plus 1 is e to the power of x times e to the power of y. And the most important for our purpose is the derivative of this function is where is this function. The derivative is a slope at the point x to this curve of this function, and so as you see all this picture is just e to the power of x. So that in green in this slide you can see the equation we want to solve, and the solution to this equation is just as a normal distribution, which is expressed through this exponential function. What's the normal distribution? The simplest way to understand what is it is by throwing balls through say regular lattice of obstacles. In the end, due to gravitation, as you see, these balls will form a certain kind of distribution, and this distribution is exactly this normal distribution. Before, we talked only about one-dimensional problem. So it's not a real motion of the drunken, it's a motion of the drunken along only a straight line. If we want to consider a real two-dimensional, in the case of the drunken man, or three-dimensional random walk, we have to introduce three coordinates, x, y, and z. Since the motion along these coordinates is happening independently on each other, the distribution function Pn of the vector r, let me recall, is an end-to-end vector of the random motion, is the product of these three distribution functions along each of these coordinates. And now consider it a diffusion. What's the difference between, say, Brownian motion and diffusion? The diffusion is happening, say, in gases, in liquids, and in solids, and in this phenomena, many particles participate in this phenomena. So that to describe this diffusion, we have to introduce, first of all, the concentration of particles. In order to do it, consider a small volume delta V. It is small but macroscopical, so there are a large number of particles inside this volume. And this number of particles is just the concentration times this volume delta V. In general, this is a complex problem, and so we start from a simplified one-dimensional diffusion, which is similar to one-dimensional random walks that we talked before. So let's introduce the time t. This is the number of steps of random walk or of each of these particles times a time t, which is needed for the one step of the random walk. So we in previous slides we derived an equation which describes the probability distribution of a random walk. We can simply generalize this equation by substituting the concentration instead of this probability Pn. Since we assume that all these particles do not interact with each other. As a result, we get a diffusion equation for this concentration C. And the value d, which is a squared over 2 tau, a is the mean square distance for one step, and divided over the time of this step, is called, this value is called a diffusion coefficient. We just derived an equation, but so far we don't understand deeply what the physical meaning of this equation. And in this light, we see that the reason of this diffusion and the nature of this diffusion coefficient is just Archimedes force. You know that on any body in a gas and in a liquid act the pressure. If we describe, if we consider non-interacting particles as we did before, the pressure is just kBt times the concentration C. This is equation of state of an ideal gas. And kB is Boltzmann constant. Consider again a small but macroscopical volume, delta V. On the left side of this volume acts the pressure pi of x. On the right side of this volume, which is at the distance delta x from the left side, acts the pressure pi of x plus delta x. And so in the whole on the body acts Archimedes force, which is the difference of this pressure times the area delta S, the transverse area on this picture. And for small delta x, it can be written as the derivative, the first derivative of the pressure, and times delta x, delta s, which is just the volume. And so far we calculated the force acting on this volume, which has n particles inside. The force per particles, per one particles, can be found by dividing this force over the number of this particle. It's F over n. And additionally, if one particle experience a force, it should move. So that the velocity of this movement is proportional to this force, and the coefficient is proportional of proportionality is the mobility of this particle. So V equals the mobility mu times this force on the particle. And now we are ready to calculate the particle flux. The particle flux which is G times delta V is the number of particles times the velocity of these particles. So it's mu times F, mobility times the force on this volume. And using an equation for this force, it can be written as minus mu times the derivative of the pressure and times delta V. At this step, we have to understand what is the reason of this force. For solids, everything is clear. If we apply a force on the surface of the surface, that's all. But in the case of liquids and gases, there is a problem of understanding. It's just because all the particles they move freely from one volume to another volume, freely all the volume. And to understand the reason of this force, consider two volumes, delta V1 and delta V2, and we see that there are particles that move from one volume to another volume, and these particles exchange the impulses between this volume. But we know, according to Newton's law, that exchange of impulses is equivalent to the forces, to some average forces acting on this volume. And so go back to diffusion problem. The particle, we just derived it in previous slides that the particle flux is proportional to the gradient of the pressure, and the coefficient of proportionality is the mobility. Substituting the pressure of an ideal gas, kBT times the concentration C, we find that the flux density is proportional to the gradient of the concentration. The coefficient in this relation is just a diffusion coefficient. This expression for the flux is called fixed fast law. And an expression that we got for the diffusion coefficient is called an Einstein relation. He was first who derived it. It says that the diffusion coefficient is proportional to the temperature T. So the higher the temperature, the higher is the diffusion coefficient and the mobility of the particles mu. And so now consider again a small volume, delta V. And so there is a flux from the left to this volume, and there is a flux from the right to this volume. And so that the number of particles is which is this volume, the change of the number of particles in this volume, dN over dt, is proportional to the difference of these fluxes. And for small delta x, we can expand this the expression g of x minus g of x plus delta x over delta x. And so we get an equation for dN over dt, and substituting n as a concentration times delta V, and an expression for the flux that we derived in the previous slide, we just get an equation for the concentration C. This is just an equation we derived before from the analogy with Brownian motion with a random walk. And this equation is called a fixed second law. So far, we considered only ideal gases. So the gases in which there is no interaction between particles. But in general, in gases, in liquids, there are such interactions. So the particles move from one collisions with another particle to another collisions. Everything that we discussed before in the diffusion equation, two fixed laws that will be valid even in this case, but the diffusion coefficient is proportional to the mean free path, that is the distance between, the average distance between two collisions, and times the average mean particle speed. That d is 1/3 L times average the velocity v. So we have a diffusion equation. And using our knowledge about exponential function, that is the derivative of this exponential function is the very function, one can easily find a solution of this diffusion equation. And by analogy with the solution we got for the random walk, this this solution is just corresponds to the normal distribution. It's written in the picture that you see here for different moment of time. Initially, at the moment t equals 0, it is assumed that all particles are at one close to one point, that are very close to each other, but with time this distribution becomes wider and wider. It's from red to green color, as you see here. And what's happened? The particle move far away from its initial positions. And so the question is how to measure this diffusion. We start with gases. To To measure it, there are several methods, and I'll talk about one simple enough method using the scalars. So you see that at one side of this scalars there is a cup in which we can place a drop of a liquid. This drop can evaporate, so its mass will be changed, and this evaporation can be measured using the left side of these scalars. And the left side, instead of cap, we have a component of the capacitor. So when the liquid evaporates, then the distance between two plates of the capacitor, it changes, but this distance can be defined from the knowledge of C of the for this capacitor. As you see on this picture, there is an oscillated circuit which has a frequency of oscillation omega, which is inversely proportional to the square root of L times C. So if the capacitor, if C is changed, that this frequency is changed, and this can be measured, and so that change of the mass of this drop dm over t is proportional to the surface of this drop and times the flux. Using expression for the flux that we have, we can find a simple expression that this change of the mass of this drop is proportional to the gradient of the concentration C. One can check that the solution of this equation, that is r squared times the gradient of C, which is constant and does not depend on r, since is C inversely proportional to the difference R from the center of the drop. Substituting in back to this equation, we get that the change of the mass with time is proportional to the concentration C of the vapor at the boundary of our drop. This is a saturated vapor concentration at the given temperature T, and is well-known value. So this equation gives us a way to calculate the diffusion coefficient. In the case of diffusion in solids, everything is much more difficult. First of all, the diffusion in solids is very, very slow. For example, to understand the corresponding value, the diffusion is by, say, 1 centimeters during the time about several days or even months. In the picture, there is a dependence of the diffusion coefficient on concentration. Along x-axis, there is a concentration of nickel-cuprum alloy, and this axis shows the relative concentration of cuprum. And you see that the value of D is very, very small. About the temperature dependence of the diffusion coefficient, it is determined by the Arrhenius law. So the diffusion is proportional to the exponent of delta E over kBT. So that here delta E is a certain activation energy, and T is a temperature, and for small t, this exponential factor is very small as well. And only for high enough t, this exponential factor can be not so small, just about 1, for t about delta E. How to measure the diffusion in solids? Probably the best way to do it is to have a narrow electron beams falling on the surface of a solid that we have. As a result, there are some, because of these beams, there are some excitations of some electronic levels there, and X-ray emissions. These X-ray emissions can be measured and considered using a spectroscope. So there are some lines, spectroscopic lines. Here the amplitude of the corresponding spectroscopic lines is proportional to the concentration of corresponding elements. And at the right on this slide, you can see the figure showing the result of such measurements. And this is X-ray macrospectral analysis of a Neelett B pair, ferrum cuprum and ferrum titanium aluminium cerium. And now about mechanisms of diffusion in solids. First of all, there is interdiffusion. So atoms can migrate from one region to another region. So consider a diffusive couple, considered of from the left hand it's cuprum, and from the right hand it's nickel, and initially they are separated, but after some times atoms of one element they are mixed with atoms of another element, and we have the concentration profiles of them shown on the picture here. Besides the diffusion of different elements, there is a diffusion of the same elements. So there are some atoms shown by letters A, B, C, and so on, and they change their position. This diffusion is called a self-diffusion. And additionally, in general, the structure of crystal body is not ideal. There are some vacancies, some holes there without atoms, and there are interstitials, and so there is a vacancy diffusion because of this, when atoms exchange its positions with vacancies, as shown here. The concentration of vacancies it strongly depends on the temperature, and this dependence is exponential, as you see here. And additionally, the rate of diffusion and the diffusion coefficient, it depends both on vacancy concentration and on the rate of such jumps, of such exchange of positions, which is exponential as well. And additionally, there are some interstitials. What does it mean? If there are some alien atoms of smaller sizes that can be placed not at the positions of the atom of the initial matrix, but between them. And so that this position can be changed, and as a result, these small atoms can be moved, diffused along the crystal. This is such a mechanism of diffusion is called interstitial diffusion. And say if we consider two different samples, each of them has vacancies inside. There is a substitution, diffusion of these different elements. So the atoms of one body moved through the boundary between these bodies and using the vacancy diffusion or interstitial diffusion mechanism. And the rate of this process, the diffusion coefficient, depends on vacancy concentration frequency of such jumpings. What's the application of this diffusion? Now, first of all, we can place some atoms of carbon on the surface of the host iron, and because of the diffusion, these carbon atoms will move from the surface inside this material. And the resulting structure will be much stronger. First of all, it will be hard to deform, since carbon atoms lack plainness of iron from movement with respect of each other. That's the first. And the second, it will be hard to crack the structure. It's just the carbon atoms put the surface into compression, since they fill all the holes in such a material. So near the surface, this material will be much stronger than before. The diffusion can also be used in microelectronics by depositing p-rich layers on the surface of n-type semiconductors. What's the difference between p and n semiconductors is just in carriers of the current. In n-type semiconductors, the carrier are electrons, while in p-type semiconductors, the carrier has a positive charge, is a holes. Because of the diffusion after heating, there appears doped semiconductors regions, which shown in blue in this picture. Finally, there is a certain summary. To make a diffusion faster, we need open crystal structure. By open, I mean that the structure should not be complex enough. The diffusion is much slower for closer packet structure. To make a diffusion faster, we may increase the temperature and consider the material with lower melting temperature, while the diffusion is slower for higher melting temperature materials. The diffusion is faster for smaller diffusing atoms, and the diffusion is slower for larger diffusion atoms. And finally, the diffusion is faster for lower density materials, while it is slower for higher density materials. Thank you for your attention.